Okay. Good morning, team. Good afternoon, team. Today, this is Integrated Math 2. We're talking about Unit 7, Lesson 1. Our goal today is just to get comfortable with some key terms, such as, let me move this just a little bit, such as initial side, terminal side, and then a vertex. All right, using that to label angles. And then also we're going to be talking about finding the sine, cosine, and tangent of an angle and what those ratios actually mean. So that's what we're going to be doing. So here we are. If you go to the folder, you'll see that I have, there's many pages of the textbook I kind of uploaded, but we're just going to focus on these few problems right here. All right, I think there's two that we're going to look at today. Three that we're going to look at today. So the solve multiple problems like problem 2 in part C. So that was a problem where we had triangles, right? And we're solving the triangle using the Pythagorean theorem. You might want to find connections between the angle measures and segment lengths in a right triangle. All right, it's helpful to think of an angle as being formed by rotating a ray about its endpoint from an initial position to a terminal position. So what this means is that you have a ray. There it is. There's a ray. Okay, let's make this a pretty color if I can. So we have our ray. Let's say it's red. Okay, and we take our ray and we rotate it from an initial side to a terminal side. So we have the starting side and then the terminal side, and then the angle would be right in here. This is our angle, 66 degrees. All right, so the point where the ray is rotated is called the vertex. So for this problem, the vertex would be B. The vertex is a point. All right. Okay. The initial position of the ray is the initial side. The initial side, usually if we're looking at a circle, I know we started talking about circles right before we went on break. Usually our initial side is always here, and we rotate from there. So we might rotate halfway around, okay, all the way around, but the initial side usually is right in here. All right. The initial position of the ray is called the initial side. The terminal position is called the terminal side of the angle. To indicate the direction from initial side to terminal side, it's customary to say to have a positive measure if the rotation is counterclockwise. So we think of a clock. So if we have a clock, there's my clock, isn't it beautiful? So we have a 12 up here, and a 6 here, and a 3 here. Remember the clock in our classroom? Oh man, I'm so sad thinking about it. So we say that if we go in the counterclockwise direction, right? It's because we say as positive measure if the rotation is counterclockwise. So if we're going counterclockwise, so against the way our clock usually goes, that's a positive angle. And if it goes down, right, the same way the clock goes, that's a negative angle. All right. So here we go. We got a diagram with the right 4 points on the terminal side, and the angle is in standard position, right? So we notice that all these points, they fall in the same line. Okay. The vertex of the angle is the origin, and its initial side coincides with the positive x-axis. All right. So the initial side would be right in here, and it goes right up here. So it says for each point, x over y, shown on the terminal side, find the ratio as y over x. Well, we know that it's x, y. So to find the ratio of y over x, this is going to be important. We talk about tangent. I'm just going to write it in there. Let's give it a little sneak peek. Sneak peek, tangent. So that's our tangent. We just divide our y divided by x. All right, so this is why I have my calculator out. Where is it? Where's my friend? Here it is. So we're just going to divide. So we would say, okay, so for the first one, we would say 8. Ah, that's wrong. We're on the wrong screen and everything. Okay, so we would say our y divided by x is 6 divided by 8. That's our tangent. Boom. Okay. Then we have 9 divided by 12. That's our tangent. Boom. Okay. 3. We have 1.5 divided by 2. Boom. What do we notice? They're all the same. And then 3 divided by 4. All right. They're all the same. All right. So we got our answers right in here. And then it says, how did these answers compare? What do you think? They're the same. Okay? The answers are all the same. Okay, why does that make sense? Well, if we're dividing our angles, right, the ratios are always they're gonna simplify the same thing. Like if we start with, let's take these two. We're not gonna do all of them, so that'd be so extra. Okay, so we're gonna take 9 over 8 and 3 over 4. So if we take 9 divided by 12, boom, 9 divided by 12, and we say, I want to simplify that. We say, oh, what's common? 3. So divide by 3, and you end up with 3 divide by 4. That's because of fractions, right? We love fractions. So that is why, because fractions. All right, next one, 4. For each point x, y in part A, suppose r is the distance from the origin to the point. How do you think the ratios x over r would compare in each case? Man, from the origin to the point. So r, why do you think we call r? Let's think about that for a second. I'm going to pause the video for a minute and really think, why, what do we know, what math term that maybe has to do with circles, right? We're doing circles, is r. So think about that. So if you've given it some thought, all right, r is for radius, okay? So whatever r is, all of these fractions, the ratios are going to be the same, okay? No matter what, let's say we're doing y over r for all these were all our y over x, right? That's what we did here. So no matter what we do, these are all going to be the same. If we look at 4 and 8 and 12, no matter how we set up our fraction, all right, all those, oh, you know what? How do you think the ratio is x over r would compare? Let's actually look at this. So let's say, so 2 over r. So let's pick a good r. What do we think? Let's say 10. Let's say here 10. And we just picked it. It doesn't matter what it is. So let's say our radius is 10. And let's get our handy dandy calculator back out. And we're going to look at all of our x values. So let's look here. X's. So x, 8, 2, 12, 4. So all these we do 8 divide 10. Boom, what do we get? One number. All right, 2 divide 10. Okay. Oh, we get another number. Okay. 12 divide 10. Okay, we get one number, and then we get 4 divide 10. 10. All right, we get another number. Oh, look, they're all different. I think the same thing would happen with the y's, right? So let's say we do 6 of the y's. y6, y1.5, y9, y3. All right, let's divide them up. I'm noticing we're getting around 7 minutes here. Okay, 6 divide 10. All right. And then, let's see, 1.5 divide 10. Okay, they're all different. Very, very different answers. Okay, so, we'll have to think about what does that ratio mean. That's going to circle back to that in a second. All right, 10 divide that. Okay, they're all different. We get different numbers, okay? So, cool. They're all different. They are different. Let's make a big, bold statement. They are different. They are not the same. If I could put a little emoji in there, I would. All right, so that's number 3. We're going to be talking about these ratios, this y, let me just highlight it, or something, because it's special, all right? So this y over x, we're going to talk about that, what that is. Oh, I gave that away is what that is. Okay, and we're going to talk about x over r, that's going to have a name, and then y over r, that's going to have a name too. So if you look through this, let me just bump up to full screen. All right, so we did problem number 3. If you look at the file, there is some work for 4 or 5. You don't have to work through this. That's extra. Okay, we're just going to be looking at right here. We're going to have some notes on tangent, sine, and cosine. Remember, I gave this one away a little bit. All right, and we're going to talk about this problem right here. So here we go. So that's some proof stuff. We're not going to get to it. So your work in problem 4, if you did work through it, which you don't have to. Okay, I didn't work through it. Shows that if px is a point, not on the origin, on the terminal side, and r is equal to square root of x squared plus y squared. Well, look at that. Where have we seen this before? We have done this. We've done it. You've done it. You just maybe forgot, but you did it. Look at this. Look at this beautiful triangle. Boom, boom. It's a right triangle. And we have the Pythagorean theorem. X squared plus y squared equals r squared. Right? Let's write this out. X squared plus y squared equal r squared. Or r is where you take the square root of these, right? R is you say, oh, I'm going to undo this, take the square root, boom, that crosses out, and then R is equal to what we have. I don't have a picture. No, it's just, man, can I beautifully take a picture of this? Let's see. Whoop. Send to the current page. That's our R. I'm cheating. I'm just taking shortcuts. So R is the square root of that. Great. So we have these ratios, okay, that I told you about, y over x and r over r, y over x, y over r, and x over r, okay, do not depend on the choice of p, meaning they don't depend on where that p is located, right? Because this can kind of be anywhere around, and you just kind of look at that shape there. So these ratios are called trig functions. I'm given special names, right? And the special names are tangent, sine, and cosine. And what's really important here, okay, is that you've recognized that tangent is called tangent of theta. Theta, that pronounced, I always have to go over this. So theta, so a lot of people start trying to say theta with an F, it's not. Theta, okay, is that symbol that's like, I'm going to draw it out for you because you could practice drawing it in your notebook or whatever, okay? So theta is a circle, boom, with a line through it. It's a Greek letter. It's an uppercase Greek letter. And so we say tangent of the angle is equal to y over x. And we say x is not 0 because if x were 0, we would be doing bad math. We'd be dividing by 0, and you cannot divide by 0. Sine, okay, is the y over the radius. And cosine, all right, the cosine of the angle will be x over the radius. All right, that's it. Boom, boom, boom. Yellow, green, purple. We're just doing colors. So for problem number 5, I think I'm going to take a whole picture of this. The terminal side is standard position with measure theta contains the given point. In each case, draw the angle on a coordinate grid, then find cosine, sine, and tangent. All right. Yeah, baby, let's do it. So I'm going to, let's see. Let's do this. Let's do it up. Do it up, do it up, do it up, do it up. Okay. Send to a new page, and let's just do it. So here we have our picture, and we're going to work through this. Okay. So here we go. I'm going to put in a little grid. I have one. So my grid's right here. All right, let's take a look at our first one. So our first one, we have the point 12, 5. Yeah, this is always the case. My grid is just not big enough, right? So I'm going to have to make it go out and say 11. Let's say that's 12. Okay, so 12, 5, and let's make a little point. So 12, 5, so we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is 12. And then 5, 1, 2, 3, 4, 5, 5. I make a point out here. Whoop, 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 whoop. Okay. And then we are going to draw the angle. So we go from the origin out. Boom. That's it. There's our angle. We can make it fancy. Yeah, we're going to make it fancy. And we could do a whoop, whoop. Okay, put a little angle in there, a little theta. And that's our angle. It says find the cosine, the sine, and the tangent. So here's the situation we're in. The tangent we know is just y over x. So if we're doing A, okay, so we're doing A, and we know we're trying to find the cosine, or we're trying to find, right, the sine, and we're trying to find the tangent. Well, we know the tangent is just going to be our y over our x, right? So our y is what, 5, and our x is 12, 5 over 12, right? So we know that's just going to be 5 over 12. Boom, done. But the issue is when we get to doing the cosine, we don't know our radius. So we gotta back up, and we gotta think of this as a right triangle. We have to think of this as being 12, and this right here was 5, right? 5 units up. And this is being 5, and we have to figure out what our missing side is, right? Well, we know that from our Pythagorean theorem, we know that 5 squared plus, I'm going to make this look nice in a second, equals our r squared, right? That's what we know. This is 2. So we know 5 squared plus r squared is equal to 2 squared. All right, here we go. And we just have to kind of undo that square, right? Square. So we just figure out that r. So we can go to our calculator, right? And I think this is kind of like what we did. We did this, right? So we do 5 squared plus 12 squared. We did this with a distance formula. It's actually a little more complicated. And then we take the square root of our answer. So we get 13. Boom. So our missing side is 13. Let me take a little picture of that so we know the math we did. In case you're like looking at this and you're like, what? What did she do? What math is she making up? All right. And we get that. Is this done recording? I want to make sure we're not done recording here. All right, so hopefully this doesn't cap out at 15 minutes. If it does, we just have to TBD. So this right here, this is 13. So our cosine, okay, we're going to be using our x over that. So our cosine would be equal to I don't know why I did all that extra stuff with those equals. It could be equal to 12 over 13. And our sine